In the next section, what we're going to be discussing is dealing with errors in different types of measurements. So we're continuing on from the last section where we talked about different types of measurements. We now want to deal specifically with the types of errors that become present when we start measuring things. And so here's an illustration of two different types of errors, the random errors and systematic errors. Random errors are just like it sounds. Here it's illustrated by a baby moving up and down on the scale, causing the scale to bounce up and down between different values. So that's kind of all random, and so it'd be a source of random error in the measurement of the weight. Systematic errors, on the other hand, are not random. They come from the fact that maybe the scale would be already set off by a certain amount of pounds. So let's say the scale was already reading 1.2 pounds before anything was put on top of it. Every measurement it makes is now going to be off by at least that much, 1.2 pounds. So that's a source of what we call systematic errors. Systematic errors can be kind of dealt with if we know how much it was off to begin with. Whereas random errors, well, as random, we don't really have a way of predicting how those are going to work. So that's what it basically says here, the two types of measurement error. Random errors occur because of random and inherently unpredictable events in the measurement process, whereas systematic errors occur when there is a problem in the measurement system that affects all measurements in the same way. So here's an example to consider. A smartphone battery is supposed to provide 3.8 volts. An aftermarket supplier manufactures 5,000 replacement batteries and finds that they have a mean output of 3.8 volts. But about half of the batteries supply less than 3.8 volts, and around half supply more than 3.8 volts. Does this appear to be a random or systematic error? Indeed, in this case, since we see they're kind of spread out, there doesn't seem to be a set amount that they're off by in every single case. This would be an illustration of random error rather than systematic error, because half of the batteries supplied more than 3.8 volts and half of them supplied less than 3.8 volts. So it appears to be a random error. And so here's another situation where errors pop up quite a bit. Scientists studying global warming need to know the average temperature of the entire Earth, or the global average temperature, has changed with time. Consider two difficulties in trying to interpret historical temperature data from the early 20th century. 1. Temperatures were measured with simple thermometers and the data were recorded by hand, and 2. Most temperature measurements were recorded in or near urban areas, which tend to be warmer than surrounding rural areas because of heat release by human activity. So with that in mind, we're going to talk about whether each of these two difficulties produces random or systematic errors, and consider what the implications would be to these errors. How could we deal with it? Is there any way to deal with it? Does the data have to be tossed out, or can we make some appropriate adjustments to it? Well, for part one, if we're measuring it by hand, if they were a long time ago, a lot of random errors could result due to the reading, calibrating, and recording process by hand. So that would be an example of random errors for when measurements are happening like that. There's a probability for that to happen. On the other hand, when talking about temperature difference due to the urban areas, this would be an example of systematic error because the excess heat in urban areas can be actually estimated to a certain degree. So we can estimate how much warmer things are in the urban areas versus the rural areas and know that that's a fairly consistent number that will be affecting every temperature measurement that's taken. The way this could be handled is in the case of systematic errors, if we can estimate how much the temperature's off by being read in an urban area, we can adjust the measurements accordingly, either up or down, however they need to be changed. In the case of random errors, there is a way of trying to get some of that randomness to be accounted for, and that would be doing some like averaging and stuff like that to help average out any possible random errors. So the more measurements taken, even if there are some random errors in there, if enough measurements are taken, we can kind of average out a large part of the random errors that were introduced. On this next example, it says, identify at least one likely source of random errors and one of the systematic errors in the following cases. And so we talked about the speed of cars are recorded by a police officer who uses a radar gun, and the accuracy of gas pumps, which measure how many gallons have been pumped. So in the first case, random errors could occur just due to human factors such as mistakes reading and recording the speeds. However, on the other hand, systematic errors could occur due to an incorrectly calibrated radar gun. So we see kind of a common theme going on here where random errors can be introduced by, say, people measuring the data that's being generated from the measuring device, whereas systematic errors can largely occur because the measuring device itself is set off by a certain amount. Now, however, in the next case with a gas pump, a random error, just one that could possibly occur, is temperature would actually affect the density of the gas. So if you pump gas when it's colder, you might get a little bit more than it reads, or vice versa. And that can kind of be random depending on the temperature. Systematic errors could occur, however, when a pump is not fixed when it gives more or less gas than it actually reports. So it might be a reading error on its part, but it would be set off by a certain amount that it needs to be calibrated back to. So it might read that it's giving more or less than it actually does. Whereas the random error in this case would be something outside of it that affects the quantity of the gas that's being drawn by the pump. So we'd like to start talking about how we measure errors. There's two ways we're going to go about doing that. Let's say, for instance, here's an example where 6 pounds are purchased of hamburger, but due to a poorly calibrated scale, you only get 4 pounds. There's two ways we can express the error here. One is by the absolute error, which is the 2 pound difference between the 6 and what was received, 4 pounds, or the relative error, which is a percentage of the absolute error to what was actually received. And so that's 2 divided by 4, so 50% would be what we call the relative error. So here are the ways we write out the absolute and relative error. The absolute error describes how far a claimed or measured value lies from the actual true value. So we say the absolute error is equal to the claimed or measured value minus the true value. The relative error compares the size of the absolute error to the true value. It is often expressed as a percentage. So we're going to write that relative error is equal to absolute error divided by true value times 100%, and then that'll convert it into a percentage. So to show how this works, let's look at these examples here and find the absolute and relative error in each case. So again, the way we're going to calculate the absolute error is by taking the measured value and subtracting away the true value. So in this case, the measured value is the 105 pounds. We subtract away 100 pounds for the true value, and that gives us an absolute error of 5 pounds. And so what we'll do next is we'll calculate the relative error. The relative error is equal to, again, the absolute error that we just calculated divided by the true value times 100% to write it out as a percentage. So it'd look like 5 pounds divided by 100 pounds times 100%. So what that would be equal to is 5 divided by 100 is 0.05 times 100% is equal to 5%. For Part B, it says the government claims a program costs $99 billion, but an audit shows that the true cost is $100 billion. So what we'll do is we'll again do the absolute error, calculate that by taking the claimed value minus the true value. And so in this case, that would be equal to the $99 billion minus the $100 billion. So what we do when we subtract those numbers, we come out with negative $1 billion. So the absolute error can actually turn into a negative number, in this case when we do the calculation. The relative error, again, that can be calculated by taking the absolute error divided by the true value. So in this case, that would be equal to negative 1 billion divided by the true value of 100 billion times 100%. So when I do the calculation here, divide the number, we get negative 0.01 times 100%. So that's just going to come out to be negative 1%. On Part C, it says the official distance for a marathon is 26 miles, 385 yards, or 26.21875 miles. But the organizers of a marathon mapped the course that is actually 26.34567 miles in length. I want to find the absolute and relative error. Okay, so the absolute error, again, what we're going to do is we take the measured value minus the true value. So in this case, that would be 26.34567 miles minus 26.21875 miles. So when we subtract those numbers, we get 0.12692 miles. That's the absolute error here. To do the relative error, again, what we do, we take the absolute error and we divide it by the true value. And we times that by 100% to get it into a percentage number. So what that's going to look like here is the 0.12692 miles divided by 26.21675 miles. And we multiply that again by 100%. So let me go ahead and show the calculator doing this real quick. We can just plug it in as 0.12692 divided by 26.21675. So we get this much approximately. We'll have to round that off a little bit. We're going to times that by 100. When I times that by 100, we come out with 0.4841, and it just keeps on going from there. So I'm just going to round this off to 0.48. Rounding that off, we get 0.48% for the relative error. Now suppose a census reports 72,453, but the actual number is 90,000. We say the number is precise since it seems to count to the nearest ones place. However, it's not very accurate since it is so far off the actual number, nearly by 25% in this case. So the actual reported census number is quite a ways off of the 90,000, even though it seems to count to a fairly small digits place. In contrast, consider a sales projection of 7.30 billion versus an actual sales of 7.32 billion. So this projection, we say this is accurate number since it's off by actually only less than 1%. However, the precision is only to the nearest tens place. It's how far it measures to a tenth of a billion in this case. So this gives rise to two things, accuracy versus precision. Accuracy being closer to the true value, precision in terms of measuring to finer and smaller increments of numbers. So accuracy describes how closely a measurement approximates a true value. An accurate measurement is close to the true value. Precision measures the amount of detail which is in a measurement. On this example, it says, suppose your true weight is 102.4 pounds. The scale at the doctor's office, which can be read only to the nearest quarter pound, says that you weigh 102.25 pounds. On the other hand, the scale at the gym, which gives a digital readout to the nearest tenth of a pound, says that you weigh 100.7 pounds. Which scale is more precise and which is more accurate? So when we consider that the true value is in this case 102.4 pounds, and if we take the 102.4 and subtract away the doctor's measurement of 102.25 pound, which would be the same thing as subtracting 102.25 pounds, we find that it's only off by 0.15 pounds. That would be the absolute error between the doctor's scale and the true scale. However, if we look at the difference between the true weight and the gym scale, what we would see is the true weight's 102.4, but the scale read out 100.7 pounds. So it's off by 1.7 pounds. So the one that's closer to the true weight is the more accurate, which would be the doctor's office. However, it doesn't read quite to as small of a pound. The gym scale measures to the nearest tenth of a pound. So in this one would actually be what we call more precise. More precise since it measures to the nearest tenth rather than the nearest quarter pound. So it has finer measurement values. On the other hand, though, it's still not more accurate than the doctor's scale. On this example, it says a new Corvette weighs 3,440 pounds. And a manufacturer's scale that is accurate to the nearest 10 pounds gives the weight as 3,450 pounds, while the U.S. Department of Transportation uses a scale that is accurate to the nearest tenth of a pound and obtains a weight of 3,428.8 pounds. So which of these is more precise and which is more accurate? So let's consider the difference between the true weight and the manufacturer's scale. So like it said here, the true weight is 3,440 pounds, whereas the measurement that was made was 3,450 pounds. So we can tell that it's off by 10 pounds. Now, if we consider the Department of Transportation measurement here, they measured it to be 3,428.8 pounds. So how far off is that from the true weight? Well, let's just do a quick calculation here. We take the 3,440 minus 3,428.8. And so we find out that the error is 11.2 pounds. So it's off by that much. So what we can say is the measurement that was done by the manufacturer, because it's closer, it's off by less, it's going to be more accurate. However, it's not more precise because this other one actually measures to smaller decimal places. So this one is actually more precise. So the general idea here is things can be more precise, but not necessarily more accurate. Things can be more accurate, but not necessarily more precise. Ultimately, we really like to have both, more precise and more accurate, and sometimes that is the case.